Hello everyone. So here we are for the fundamental theorem of calculus day 2. And the fundamental theorem of calculus before told us about the definite integral, where we didn't have plus c anymore, but instead we plugged in those numbers that were on the interval to find out what the area was under the curve. Remember, every time you see an integral, you should think area under a curve. Now, this is really the fundamental theorem of calculus day 2. Now, it depends on what source you're looking at for what they call this. Sometimes they will call it the second fundamental theorem of calculus, or you'll just see it's called the fundamental theorem of calculus part 2. Depends on, again, what source you're looking at, whether it's the book or online or Khan Academy or whatever. So it's the same thing, it's just named weirdly, I guess. So what the fundamental theorem of calculus, the second part, says, and it's a little technical, so I'm going to try to explain it the best that I can, that if you have a function that's continuous over a certain interval that contains a being a number, then for every x in that interval, this is going to be true. Now, all this is saying is that if you take the derivative of the integral, you'll get the original function back. So it's really just saying that the antiderivative and derivative are inverses of each other. So if I would have, let's say I would take like the integral of 2x plus 3 dx. Well, that's going to be x squared plus 3x plus c. Well, then if I take the derivative of that, I'll get the original back, 2x plus 3, that these are going to be the same. That's all that the fundamental theorem of calculus is telling us. So if you are given a problem where they say, for example, capital F of x is this wonderful integral right here. If I want to find the derivative of that function, so I want to find the derivative of that, you have to ask yourself a few things. First of all, is this continuous? Okay, is that continuous? And we know parabola, that is going to be continuous, yes. Really, the only thing you have to worry about are asymptotes, and as long as the asymptote is not happening in your interval, then you're okay. But is this continuous? Yes. Is this a number? Yes, it is a number, and that can be any number, because remember, the second fundamental theorem of calculus just told us that you had to have that a. A could be anything. So, is that a number? And lastly, is this just x? If that's true, then to find the derivative of this is actually the same thing. You just take x and plug it in for t. So you just plug in. So that's going to be x squared plus 2x. You don't need the c, because when you take the antiderivative, you add the plus c in, and then when you retake the derivative again, the derivative of c is 0, so it goes away. So again, this is not asking for f of x, it's asking for f prime of x. It's asking you to take the derivative of the integral. So when you take the derivative of the integral, you just plug in x. Okay? So the question then becomes, well, what happens if this number up here is not just x? This is not x. Okay, but this is still going to be continuous. Now, I know there is a vertical asymptote at t equals 0. However, that's 0 is not included here. From 2 to x squared, that's going to be all greater than 0. So we're still good. It's still continuous. And this is still just a number. So if you notice on your slides, I don't know if you printed them out or not, but this problem and the next problem are exactly the same. So I'm going to show you how to do this without the second fundamental theorem of calculus and with the second fundamental theorem of calculus. Without it. So first thing we're going to do is we're going to find capital F of x. So I'm going to take this antiderivative. So first I'm going to rewrite it from 2 to x squared. I'm going to rewrite it as t to the negative third dt. And now I'll take the antiderivative. So I'm going to add 1 to my exponent, making it negative 2. Then I'll divide by that negative 2. And then we're going to take it from 2 to x squared, just like we did last week. So I'll have 1/2 x squared to the negative second minus negative 1/2 2 to the negative second. So this will be negative 1/2 x to the negative fourth, because whenever you raise an exponent to another exponent, you multiply. And then 2 to the negative second is actually 1/4, so this is going to become plus 1/8, because 1/4 times 1/2 is 8, and negative times a negative becomes positive. So I have this. So f of x, capital F of x, is that. I've taken the antiderivative. But now they want me to take the derivative of this. So I can take the derivative of my answer, and using my power rule, this will become 2x to the negative fifth. And then the plus 1/8 will become 0. So this is my final answer, f prime of x. Now this was without the fundamental theorem of calculus, the second fundamental theorem of calculus. This was just the straight taking the antiderivative, doing the integration, plugging in our numbers, subtracting, just like we did last week. We just had an x in there instead of having numbers, okay? But this was exactly the process that we went through. Now, what the second fundamental theorem of calculus tells us is that I can just plug that in. I'm still going to rewrite this. Oops. I'm still going to rewrite this as 2 to the x squared of t to the negative third dt. Now, since this down here is a number, this was continuous, we said, except for the vertical asymptote, but that was at 0, so that's not included in our intervals, so I'm good there. Now I'm just going to plug this in. So that gives me x squared to the negative third. Now the only difference here is, way back at the beginning with my theorem of calculus, this was just x. I could just plug x in and I was good to go. Now, since it's a function, it's x squared, and this would be anything besides x. So maybe you'll have x plus 1 or x plus 4 or whatever. If you don't have just x, the only difference is you just then have to do the chain rule, which is multiplying by the derivative of whatever that is. And the derivative of x squared is 2x. So this becomes x to the negative sixth times 2x, which is 2x to the negative fifth, which you can see is what we got the first time. So going through the antiderivative, going through all the antidifferentiation, you can always do that. The second fundamental theorem of calculus just gives you that shortcut. You can just plug in because you're taking the derivative of the antiderivative. So when I take the derivative, I have to do the chain rule. That's why I have to do that extra step, because when we take the derivative of something, we've learned the chain rule before. You always have to multiply by the derivative of the inside. Well, that's exactly what we're doing here. When you take the derivative, you have to multiply by the derivative of the inside. So that's why you have to do that extra step. But still, using the second fundamental theorem of calculus, it does save you some work. Okay, I think we only have 2 more problems. Yep, I should be able to get it in under the time limit here. Okay, so now this one is not finding the derivative. Okay, so I can't use my second fundamental theorem of calculus because I have to find f of x, capital F of x, not f prime. If they were asking me for f prime of x, and I'm going to write it down here at the bottom, if they were asking me for f prime of x, then I could just plug right in. This is continuous, everything is good. It would be x cubed plus 2x minus 2. I would be fine with that. but they're not asking for that. Instead, they're asking for f of x. So I'm going to do the anti-differentiation like we did last week. So I'll add 1 to my exponent and then divide. So I'll have 1/4 t to the 4th plus t squared minus 2t. I'm going to take that from 2 to x. And so I'm just going to plug x in wherever the t's are. So I'll have 1/4 x to the 4th plus x squared minus 2x. That's my first part. Now I'm going to subtract when I plug in 2. Plus 2 squared minus 2 times 2. So my first one here is not going to change. It's still just going to be 1/4 x to the 4th plus x squared minus 2x. But then my second one here, let's see, this is going to be 4 plus 4 minus 4 is just 4. So there you go. You're going to have minus 4. So f of x, capital F of x, I'm sorry, I keep saying f of x when I mean capital F of x, is going to be 1/4 x to the 4th plus x squared minus 2x minus 4. Now notice, if I wanted to take the derivative of this green equation here, it would give me x cubed plus 2x minus 2, which is what we said it would give me. The fundamental theorem of calculus skips all that green and goes right to that purple. Now, this is what we were looking for here, so I couldn't use that theorem, but there we go. And now this last little part, they did ask me to find capital F of -1. So capital F of -1 just means I'll plug in -1 to all these places. So -1 to the 4th plus -1 squared minus 2, minus 4. Oh, I'm running out of room. 4. Okay, so this is going to be 1/4 plus 1 plus 2 minus 4. And that's going to give me -3/4. Okay, so if they're not asking for capital F prime, you can't use the second fundamental theorem of calculus. It's only when they're asking for capital F prime. Okay, and finally, this last one. So now they are asking for capital F prime. However, notice that my bottom number is not a number. It's a function, not a number. So we cannot use the second fundamental theorem of calculus for this one. We cannot just plug in because there would be 2 things to plug in. So we can't do that. Because the reason why we can do that earlier when this is a number is because when you plug that number in and then they take the derivative of that number, it becomes 0. So that's why it doesn't matter what that number is, because when you take the derivative of it, it becomes 0 no matter what. But now that it's a function, it's -x, it does matter. So we have to go through the entire integration process. So when I integrate here, I add 1 to my exponent and then divide. So this will give me t cubed plus 2t. And it's going to be from -x to 2x. And now I just have to plug each one in. So I'll have 2x cubed plus 2 times 2x. And that's my first function. And then I'll plug in -x. So I'll have -x cubed plus 2 times -x. And we're going to subtract that. So this becomes 8x cubed plus 4x minus -x cubed minus 2x. So I'm going to distribute that negative plus x cubed plus 2x. So that's going to give me 9x cubed plus 6x. Now remember, all of this was just capital F of x. All I did was do the integration, but they're still asking me for the derivative. So my final step here is I have to take the derivative. So that gives me 27x squared plus 6. Whoops, that didn't really work very well. How can I get that down? There we go. Okay, so our final answer there is 27x squared plus 6. So going back to the very beginning, for the second fundamental theorem of calculus, remember, if they're asking for capital F prime, you first have to say, is this continuous over the interval given? Is the top one just x, and is the bottom just a number? If it is, you strictly plug in. If this top number is not just x, but instead a function, then all you have